Welcome to Introduction to Machine Learning. In this lesson, we'll explore how machines learn from data to make predictions or decisions. Think of it as teaching a computer to identify patterns without explicitly programming every step. This module belongs to Fundamentals of Machine Learning, part of an AI practitioner pathway. We'll cover the basics of supervised, unsupervised, and reinforcement learning, and discuss how they differ from traditional programming approaches. By the end, you'll understand the core principles and why machine learning has become so impactful in our world. Machine learning is the science of enabling computers to learn from data and improve over time. Rather than giving a computer rigid instructions, we feed it examples or experiences so it can discover patterns or rules on its own. This definition opens the door to innovative applications, from predicting the weather to recommending movies or diagnosing diseases. By focusing on data rather than hard-coded rules, we empower computers to adapt and evolve as circumstances or inputs change. In traditional programming, we specify rules for the computer to follow. If X is true, do Y. Machine learning flips this concept. It takes inputs and corresponding desired outputs, letting the system infer the hidden rules. It's more like teaching a child to recognize shapes by practice and experience, rather than instructing them to memorize complicated geometry formulas. This difference allows ML systems to handle complex, ever-changing data scenarios that would be too cumbersome to manage with strictly defined instructions. At its core, machine learning is about transforming raw data into insights. The process involves gathering data, cleaning it, selecting a model, training that model on historical data, evaluating performance, and iterating to improve results. Think of it as a learning loop. Each round of training and evaluation refines the system's ability to detect patterns. This loop is the beating heart of any machine learning project, enabling computers to make better predictions or decisions after each wave of feedback. Supervised learning is like having a teacher provide the correct answers. You have labeled data, examples with known outcomes to train your model. For instance, consider an email spam filter. You provide historical emails labeled as spam or not spam, and the model learns how to distinguish. Later, when you receive new emails, the filter applies those learned patterns to classify messages automatically. Common supervised learning tasks include regression for predicting continuous values and classification for predicting discrete categories. Unsupervised learning happens without labels, much like exploring a new city without a guide. The system looks for hidden structures or patterns in unlabeled data, finding clusters, associations, or anomalies. Imagine a music streaming service grouping songs by similarity to recommend new tracks. The platform analyzes listening habits to group songs and listeners with comparable preferences. No one tells it exactly what music groups should look like. The system discovers these groupings on its own based on patterns in the data. Reinforcement learning is inspired by how animals learn through rewards and punishments. A model or agent interacts with an environment, learning which actions lead to the greatest long-term gains. It tries different strategies, gets feedback like points or penalties, and refines its approach. A famous example is AlphaGo, which learned to play and eventually beat world-class Go players. By continually adjusting based on wins or losses, the system self-optimizes its strategy for the best possible performance in that environment. Imagine a small bakery wanting to reduce wasted pastries at the end of each day. Initially, the owner guesses how many to bake, sometimes overestimating, sometimes underestimating. Introducing a simple machine learning model changes that. It learns from historical sales, weather patterns, and local event calendars. Soon, the owner bakes closer to the perfect number of pastries, cutting both costs and waste. This transformation shows how ML can make everyday operations more efficient, even in a cozy neighborhood bakery. Visualize a simple flow chart: data input, model selection, training, evaluation, feedback/refinement, predictions or actions. Each stage in this cycle feeds into the next. A bar chart might compare different models' performance metrics, like accuracy or error rate, providing an instant snapshot of which approach is best. These visual aids help make complex processes clearer. With diagrams, students can grasp the iterative nature of machine learning and how continuous improvement is built in at every step. Facebook uses machine learning to personalize news feeds. It analyzes user interactions, likes, comments, shares, to infer what's most engaging. Supervised models classify posts as relevant or irrelevant, while unsupervised techniques group users with similar interests. Reinforcement algorithms fine-tune updates in real time, ensuring the feed remains enticing. This is why two people can look at the same platform but see entirely different feeds. By understanding this real-life example, students can connect ML concepts to familiar daily experiences. For those exploring machine learning further, websites like Kaggle and the UCI Machine Learning Repository offer datasets and competitions. Showing a screenshot of Kaggle's interface can motivate learners to try out projects. These platforms provide datasets on housing prices, retail sales, medical research, and more, perfect for practicing skills taught in this lesson. Whether you're tackling a beginner challenge or delving into advanced competitions, these online communities provide valuable feedback in learning experiences. Data is the lifeblood of any ML project. Quality datasets, clean, well-structured, and representative, are crucial for producing accurate models. For instance, you might have a retail transaction dataset where each row represents a purchase, complete with timestamps and product categories. The better the data, the clearer the patterns a model can detect. In many cases, preparing these datasets, removing duplicates, handling missing values, and normalizing formats takes more time than the model building itself. Good data hygiene is essential. Beginners often start with languages like Python or R, thanks to extensive machine learning libraries. Tools like scikit-learn, TensorFlow, or PyTorch simplify model creation and training. These libraries provide ready-made algorithms for classification, clustering, deep learning, and beyond, including short video screenshots of code examples, such as a few lines for training a regression model, can demystify ML for newcomers. The goal is to show how accessible these tools can be once you know the fundamental concepts. Even in well-planned projects, surprises arise. Consider a marketing team training a model to predict seasonal trends. They forget a major cultural event that significantly changes purchase behavior. Without accounting for that data, the model fails to predict a critical sales spike. Through small stories like this, we highlight that machine learning isn't magic. It needs continuous updates and real-world context. The lesson: never overlook the domain knowledge around your data and the real-world factors influencing it. In this lesson, you've learned the basic definition of machine learning and how it differs from traditional programming. You explored the three main types: supervised, unsupervised, and reinforcement learning. You saw how real-life examples like social media news feeds or bakery sales illustrate the power of data-driven predictions. You also glimpsed essential resources, Kaggle, UCI, and realized the importance of good data quality. Equipped with these fundamentals, you're ready to explore more in-depth concepts and techniques. Machine learning powers many of the applications you use daily: personalized recommendations, fraud detection in banking, automated chatbots, and even medical diagnosis. By employing ML, organizations improve customer experiences, reduce errors, and uncover new insights hidden in large amounts of data. Whether it's reducing waste in a bakery or helping doctors spot critical symptoms, machine learning has practical, life-changing benefits. As you continue your journey in AI, remember these core ideas and keep refining your skills with hands-on practice. Beyond personal convenience, machine learning has profound global implications. It supports climate modeling, advanced robotics, sustainable agriculture, and cutting-edge scientific research. With climate models, for instance, ML helps predict severe weather events and suggests preventive measures for communities at risk. In agriculture, it optimizes irrigation and crop management through satellite imagery and sensors. When you grasp these possibilities, you see how your knowledge can contribute to solutions for some of humanity's biggest challenges. Congratulations on completing this introductory module. You've built a solid foundation in the concepts that power machine learning, an essential skill in the AI practitioner's toolkit. Going forward, you'll dive into more advanced topics like deep neural networks, optimization techniques, and specialized algorithms. By staying curious and actively practicing with real data, you'll transform from learner to practitioner. Remember, machine learning is a journey of continuous discovery, so keep exploring, experimenting, and evolving. See you in the next lesson.